Hello, hello everyone. Although no one is listening to me. Okay, so this is the question. Says consider two-level cache hierarchy. Okay, so there are two-level cache. So there is that CPU, and on that CPU there is a RAM. Actually, no. First it goes cache. So there is this CPU that will go to cache 1, and then it will go to cache 2, and then it will go to RAM. Let's say RAM. So there are cache in two level. Okay, then there's CPU. Now what is happening? Let's see what is happening. So there are two cache. Okay, and in application incurs 1.4 memory access per instruction on average. So what it does is, if there is one instruction, then it needs one memory access. Means what does it means? It means that it needs 1.4 for one instruction. It needs to access memory, which can be probably cache. Most probably that would first go to cache, right, for memory access. After that it will go to your RAM. Okay, so first of all it will go to cache, right? So right, okay, so 1.4 memory access, right? And first it will go to cache L1, then it will go to L2, and then it will go to RAM. So 1.4 memory access will be needed. Okay, per instruction on average. For this application, the miss rate of L1 is 0.1. Important right here. Okay, so miss rate of L1 is 0.1, right? इसका miss rate कितना है? What is the miss rate of this cache? 0.1. And L2 cache experience on average 7 और इतना. Okay, the miss rate of L2 expressed to two decimal places is what? Okay, so let's try to find out the miss rate of L2. That's what it's saying. So there are 1000 instruction, right? And what we just learned, it needs 1.4 memory access. So what is miss rate first of all? What is average miss rate here? So miss rate is nothing but number of misses, okay, upon number of hit plus number of miss, right? Easy concept, nothing too new here. Okay, so this is it. And 1.4 memory access is needed per one instruction. Okay, and there are 1000 instruction that need to be uh, executed. So 1000 into 1.4 means 1400. These are the number of instruction that will be executed. Sorry, these are the number of memory access that will be needed, right? No problem. Now we need to find miss ratio of L2. Okay, so the let's say that application is loaded right here. It's loaded right here. The application is right here. Okay, the application is here. Okay, so the application is loaded in the CPU, and it is sending the 1400 instructions. Okay, sorry, 1400 memory access. It has done what? It has executed 1000 instructions. Now it is sending some 1400 memory accesses. Okay, so out of those 1400 memory accesses, okay, its miss ratio is only 0.1, meaning its hit ratio is 0.9, but we need miss ratio here. So only 140 instructions on average, only 140 instruction will not be found on cache L1, right? Only 140 instruction will not be found in cache L1. So in this case, what will happen is this CPU will go to cache L2. Now, this was the case for L1, 1400 were the misses. Now it will come to L2. So there are total 140 instructions, right? So what we are giving that there are seven misses according to 7 misses per 1000 instruction of the application. That is the data we are given. Note that per 1000 instructions. And for 1000 instruction, memory access was 1.4 on average. So per 1400 memory access, there are 7 misses. And also in that, only 140 instruction on average are coming to cache 2, meaning there are 7 misses in 140 instruction. So that is 1 upon 20, and this would be 0.05. So the answer right here would be 0.05. And this is the solution of the first multi-level cache problem. Okay. All right. Next, in a two-level cache system, the access time of L1 and L2 caches are 1 and 8 clock cycles. So, okay, in two-level cache systems, again, there is L1 level and L2 level, and there's a CPU, same diagram as before. There's coming in L1 level and in L2 level, and there is a RAM, and it is like this. Okay, the access time of L1 and L2 cache are 1 and 8 clock cycles. Meaning access time of L1 is 1 clock cycle and access time of L2 is 8 clock cycles respectively. The miss penalty of L2 note miss penalty of L2 cache to main memory is 18 clock cycles. Okay. Okay. Meaning, what conclusion we can draw from here? So, what is miss penalty? Right. First of all, what is miss penalty? So, if Elvin misses, then the time that it takes is miss penalty. So, CPU will try to reach. First of all, it will try to reach Elvin in 1 clock cycle, right? And it will have certain hit miss ratio. Okay. So the miss ratio will happen, right? The miss probability will happen, and after the miss has happened, what will be the miss penalty? It will be 8 clock cycles, right? It will be 8 clock cycles. So 1 plus 8, this will be the total miss, right? Then there will be RAM, so 9. The miss rate of L1 cache is twice that of L2. Hmm. Average memory access time of the cache system is 2 cycles. The miss rate of L1 and L2 are respectively. Okay. Okay, so it is like real mathematical right here. So there is L1 and L2 and CPU. It is sending there, RAM. Okay. And average memory access time. What is formula of AMAT? AMAT is miss ratio into time for L1 first of all, one second, one second. If we want it in miss ratio, we want miss rate of, right, miss rates. Okay, so we will use miss rate. First of all, 1 minus miss rate, this is hit rate, then time of L1, then time of L1 plus miss time of L1, right, miss time of L1, this miss has happened, miss time of L1 into miss 1 into hit 2 time of L2 plus miss 1 time of L1 plus into miss 2 time of L2, ये होगा एवरेज मेमोरी एक्सेस टाइम. So let's just put values here. The miss penalty of L2 cache to main memory. L2 cache to main memory. Miss penalty. So what is miss penalty of L1? Miss penalty of L1, huh? So miss penalty means it has already missed. So it has already missed. Means hit did not happen. So
खाना थोड़ी देर में खाओगे?
नहीं,
दाल रोटी सब्जी
नहीं.
हाँ
मिस
खा ले जाए.
miss has already happened. So it's either hit on L2 or miss on L2. And RAM already RAM already has it, right? Okay, so this is 18. Let's try to open it right here. This right here is 18. One. This is L1, right? What is L1? It's not possible. Hmm. This is. We'll have to try it again. Okay. Let's try to do this question. It is a recent one. It is GATE 2023. It says in 8-way set associative cache of size 64 kilobytes. So 64 is nothing but 2 raised to power 6. Kilobytes means 2 raised to power 10. And byte means 2 raised to power 8 is used in a 32-bit address. So we know the physical address size. It is 32. Okay. So let's assume it is byte addressable memory. So 2 raised to power 6 into 2 raised to power 16 bytes. And it is the address is subdivided into tag, index, and block offset. Number of tag bits are okay. So it is 8-way set associative, right? Yeah. And the block offset is size of line. What is the size of line? It is in 8-way set associative. So size of line must be the number of tag bits. The block offset, tag bits. The tag bit does give us Wait a second. 4 should be. It is direct mapping, not direct mapping. It is set associative mapping. So there is word offset. Okay. It is byte addressable, right? So let's assume line size to be 1 byte. So 64 upon 2 raised to power 6 and 2 raised to power 6 teen. 19 should be the answer. Okay, so this was last for today. Today I will try to do till 1 hour for sure.